So tonight we are looking at a class of galaxies in the Virgo cluster, so 50 million light years away. Class of galaxies called Dwarf Elliptical galaxies. They are relatively low in luminosity compared to the Milky Way. That's what the term dwarf means in this context. Low luminosity galaxies. They're elliptical in shape, apparent shape, and ellipsoidal, probably in three-dimensional shape. And for a long time, they've sort of been a source of mystery, enigma as to exactly what causes them to form in this way. This class of galaxies is really not seen anywhere, except pretty much not anywhere except around other big galaxies. So especially around in clusters of galaxies, you see them. So that you see them in the Virgo cluster, which is the nearest cluster of galaxies to us, and you see them in the Coma cluster, which is further away. I think they're seen in the Fornax cluster, but Virgo is sort of the best place for us to study them. My own association with these galaxies goes back at least 20 years. I had a PhD student who finished her PhD in 2003. She did a PhD thesis on these galaxies. She finished 20 years ago, so it probably goes back 25 years. My work on these galaxies, but they've remained as mysterious as ever. One of the people leading this run is Elisa Toloba. She'll be joining in a few minutes. She was my postdoc many years ago, but before that, she did her PhD thesis in Spain on this class of galaxies. That's what I had a different student do a PhD thesis on these galaxies. That's what led to my association with Elisa. She knew I'd worked on these galaxies before her PhD thesis with a different student, and so she came and did a postdoc with me. And here we are continuing in our attempts to understand these galaxies better. So we'll be taking spectra tonight. We are taking spectra already with ESI, the Echelle Spectrograph and Imager. And near the end of the night, after this STS session, near the end of the night, the Virgo cluster will, for the last hour and a half of the night, the Virgo cluster will no longer be accessible. It'll be too low in the sky for the Keck telescope to access, too close to the horizon. And so at that time, we'll switch over and do a different, we'll get spectra of RLR stars in the Milky Way for the last hour and a half of tonight. And we'll have a very similar drill tomorrow night, where we'll do Virgo cluster galaxies for most of the night. But for the last hour and a half, the Virgo cluster is no longer accessible. Too low in the sky. We will get spectra of RLR stars in the Milky Way. And I'd be happy to put a link in the chat about recent RLR study. Oops, I'm so sorry. Is my audio cutting up still?
It is a little bit.
Sorry about that. It must be my hotel Wi-Fi bandwidth. I'm traveling today, so sorry about that. Thank you for letting me know. Please let me know if I should repeat anything. But what I will do is I'll put in the chat some of the work we're doing with RLR. It's a recent press release. Well, not so recent, January, but January of this year. I'll find that link and put it in the chat. Again, apologies for the bandwidth. There's our Elisa. Oh. Let me find the link and put it there. Sorry, the link didn't come through when I copied. Here's the actual link to our Larry story from a few months ago. Morning, Annalisa. It must be quite early in the morning for you. Maybe not super early.
Good morning, Prof. Raja. No, no, it's not so early. It's 8:30 right now, or 8:40 if you want to be more precise. It's quite convenient. It's just a matter that I had a bit of a battle with a Zoom link. I deregistered for one of the meetings and it looks like it threw everything out. But so I had to re-register. It took a bit of time, so I'm a bit late, but thank you so much for arranging another session.
You know, our science team, you're most welcome, Elisa. Our science team is going to join. We were on a different link, on the Keck Zoom link, but they're going to join this one.
Thank you so much.
And what I just put in the chat, I don't know if you saw this in the chat, I just put a link to some of our work with RLR stars, and we had a press release about that in January. That's the link I put. I don't know if you can see that.
Yes, I saw it. Thank you so much.
Okay.
I've been playing with the universe, and I saw that there's some variety, can I put it, of projects going right now. Some of it on galaxy classifications like you've proposed, but there's also other ones where one can do light curve classifications. I think there are 2 that are running.
I see.
And some of those, of course, would then also be in the domain of these variable stars like the RR array and so on. But then I started reading up and see there's actually a host of these different ones with instabilities and so on. So in the survey that you've done right now, did you see anything that's peculiar, or is it just more run-of-the-mill type stars?
You know, it's hard to tell, Annalisa, because we don't have that many measurements per star. You know, we have between 35 and 40 measurements per star for this survey. We are also working on another survey where there's more like over 1,000 measurements per star, 1,500 measurements per star, but many fewer stars. And there, that's a better place for us to look for anomalies. Well, I guess what I'm trying to say is with only 35 to 40 measurements per star, it's difficult to tell sometimes whether something is a standard variable star or something unusual. The main contaminants we get are quasars that are long period variable that don't have periodic variations. Long-term aperiodic variables. That's the main contaminants. Those are the main contaminants we see. But there are certainly other exotic kinds of variables, you know, rare variables that are exotic but periodic, and those we haven't been able to find with this data set. But I'm hopeful that we can find it with the other data set, the one with where we have 1,500 objects, 1,500 epochs.
When you say this is a survey, I'm just wanting to know, I saw some of these automated surveys that actually give one access to the data. So, I mean, that's how we also now end up classifying some of these under this universe type thing. So I was wondering, would these data be accessible or not?
Generally, yes. The Pan-STARRS 1 data are accessible. That's one of those time domain surveys. Our NGVS data, the raw data are always in the time domain. Sorry, the raw data are always in the public domain, but the processed data may not be, meaning there's a lot of cleanup that goes on to achieve better calibration of the data and those sorts of things. There are many public domain time domain data sets. The Pan-STARRS 1 is one of the best examples, PS1, Pan-STARRS 1, not PlayStation, but Pan-STARRS. I'll put the name in the chat. Yeah, this survey, it's an STARRS is an acronym that I'm not remembering, but even the acronym has often been shortened. You'll often see it shortened to PS1. This is a survey that covered 3/4 of the sky. It was a time domain survey. I'm going to take a quick moment to check in on to see why Elisa and Chensu and others haven't joined this Zoom link. Let me check. I'll be right back. All right, I sent them an email. Let's hope they. Yeah, hi, Johanna. We've started, but we're waiting for the science team to join. Thanks, Robert. Yeah. What I'm going to do is I'll share my screen, and we're looking at the Virgo cluster. I have an image of the Virgo cluster that I'd be happy to share. We're taking spectra tonight of a certain class of galaxies in Virgo called Dwarf Ellipticals. You probably saw that in the write-up. But yes, we're looking at a class of galaxies called, putting this in the chat, Dwarf Ellipticals. I sent the science team the link that I got when I registered. That's why it's showing me twice. I'll ask them to rename themselves. Is that you, Arena?
Yes,
You know,
hello.
because I registered for Zoom,
Yeah.
get this link. It is you under my name. There are many versions of me, so you're welcome to rename yourself. You know how to do that. I assume there's 3 buttons and 3 dots in the upper right here. I'm replicating rapidly here. Many versions of me. This is the danger of sending out a link. When you have these room registration systems, it remembers the name of the
Cloning is
person who registered.
apparently real.
Cloning is real. Let's see. Let's see who else has joined with the link. I think Elisa has joined, and maybe Chanshu. Hi, Elisa. It's named you. It's put my name against you, Elisa, because I sent you my registration. So if you just rename yourself, then people will see what your name is. The 3 dots in the upper right of your Zoom thing will let you rename. And I think Chanshu, please do the same. There we go. So Elisa's connecting from Northern California. I'm in Arizona. Rena's in Hawaii. Chanshu is in Hawaii. Different places in Hawaii. Rena and Chanshu. Mountaintop and Keck headquarters.
Yeah, Rena is doing all the hard work. I'm just sitting in the headquarters.
That is not true. I'm just watching the weather. Kinsu gets the short end of the stick if something goes wrong with the instrument.
And we are recording this session. Arena, I would love for you to introduce yourself and the work you're doing. Same for Elisa, same for Chanshu. So
Sure,
why
yeah.
don't we start with you, Arena? We'll just
Hi,
take it away, please. Yeah.
I'm Arena. I'm one of the telescope operators here at Keck. So, I'm primarily responsible for moving the telescope, making sure we get on target, checking pointing, making sure, the guiding goes, we're guiding well through the night, checking things like that. And then also, of course, keeping an eye on the weather. That's one of the main things I do. Make sure we don't get any fun snow or rain or high winds and dust getting into the dome. So, I have a bunch of weather cameras open and just kind of keeping an eye on the skies. So for example, tonight we actually have a little bit of instability. We started the night out with fog, so we opened a little late. And things are still not super stable, but hopefully they'll stay that way so that Raja and the team can get lots of good data. And I think that's it, unless you want me to say something else, Raja?
That's great. Thanks, Arena. Thank you very much. Chanshu, you're next.
Hi everyone, can you see me? I'm Jianxiu, so I am a support astronomer. So my job is mostly when there's like observers. So I'm kind of like a contact person. So to help the train the observers to use instruments. And then whenever there's like instrument has some issues, I just try to help them to resolve those issues to make sure that observing is going on well. And sometimes when observer has questions like before the round or after the round, when they want some help to do data reduction, I can also help them on that. So that's most of my roles during the nighttime observations.
Thank you, Chanshu. And let's see. And you're in Waimea at Keck headquarters in remote ops too, right? The remote ops.
Oh yeah, sure, right. So actually we have a kind of like remote observation room. You probably cannot see it because my background is a little blurred, but so we have like 2 telescopes at the summit, and then for each of them we have like remote observation room at the Waimea, which is on the big island of Hawaii, and then it's close to the beach, so it's really nice. because you don't need to go to the summit and suffer from those some of the high altitude sickness. So it's kind of like easier to conduct observation here, especially you are staying up very late during the night, and then you probably are not thinking pretty well. So it's a little bit cozy to observe from the headquarters in Waimea. And then during COVID, we also have some like enabled capabilities to connect to the observatories from like literally anywhere. So that's where most of the observer will use. So sometimes we have the observers on site, but sometimes we can also accommodate like remote observations, just like tonight. So everybody can hop on the Sun and then view what we're doing using the Sun, and then remote connect observing somewhere.
Thanks, Chenchu. I was wondering if Elisa, whenever Elisa has a moment, I'll ask her to share her screen and also introduce, but first introduce and then share her screen. I've met most of you before, not all of you. My name is GuhaThakurta. I'm a professor of astronomy and astrophysics at the University of California, Santa Cruz. And I've been studying galaxies for most of my professional career. And I was saying to the group a little bit earlier that I've been studying dwarf elliptical galaxies for nearly a quarter of a century, going back to the late 1990s with Keck and with ESI even. So it feels like a full circle moment. This observing run does. We're still trying to crack the mystery of these galaxies. We're getting different kinds of data, different galaxies. There are many dwarf elliptical galaxies, of course, in Virgo. We try to collect bigger samples, better samples, higher, greater data quality, all those things. So, hey, Elisa, I'm going to keep quiet now and ask you to introduce yourself, please.
Oh, okay. So I'm Elisa Toloba. I'm professor at University of the Pacific in California. And I did well, I'm originally from Spain, and I did my undergrad in physics and astrophysics in Spain, and my PhD also in Spain. And then I moved to California and never left because I just love it here. So I have been studying, actually we are observing tonight dwarf ellipticals in the Virgo cluster, and that was the topic for my PhD. So we are basically doing a follow-up on the same kind of research that I have been doing. So these are galaxies that are very dear to me, that I know by name and that I know who they are. Yeah, so what we are focusing is on their stellar population. So these dwarf galaxies are basically amongst the very first galaxies that were formed. So these are like the building blocks of larger galaxies. So studying the properties of these smaller galaxies, we have a better understanding of galaxy formation and evolution in general because of these building blocks. So you need them to then generate much more bigger galaxies. They are also the most abundant in the universe, dwarf ellipticals, and they are by far higher in number than any other galaxy type. So tonight we are trying to get their stellar population. So that means the star content. So we are trying to see what kind of mix of stars are in these galaxies, because that tells us information about how they evolve, because stars have very specific, depending on how mass massive they are. If they are very massive stars or they are smaller stars, they have a very specific time scale of dying, right? Of their life and dying. So that gives us a lot of information of how, knowing what is the mix of those stars, how these galaxies have yeah. So that's basically what we are doing tonight.
Elisa, one of the things I was thinking about is I'll say a little bit about KCWI and IFU's data, but are you able to share your screen, please, Elisa? That would be terrific.
Yes.
Are we on the second science galaxy now?
So we are in the second galaxy. How do I know in which exposure are we?
You'll see number left.
Yeah, I think we're still at the first exposure. So if it's like going to the second one, you'll see the number be 2, and if the last one, there will be 1.
Oh, okay. So because it says number of exposures 3, it means that we are in the first one.
Yeah, right.
So I am not able to share my screen. Disabled participant screen share.
Oh, let me do that. Sorry.
Okay.
Lisa, I'm going to make you co-host, and that will allow
Okay.
you to share your screen. Just give me a second.
Mm-hmm.
You should be able to share now. Sorry.
Okay.
Thank you. Oh, wow. So you're doing 3 half-hour exposures, total of an hour and a half?
Yes.
Okay, perfect. And this galaxy, as you can see, is called VCC 0882. VCC stands for Virgo Cluster Catalog.
Mm-hmm. And the galaxy is right here in my cursor. The one that we are observing.
I can't
this
see
very
it.
fuzzy. Yeah, because this is M86 and it's
That's
so
taking up all the
so that's
contrast.
why.
Yeah. Oh, that's M86 up there? Wow.
Yes.
M86 is the galaxy that's due south of M87, right? M49 is the other one to the upper right. Let me see.
I know this is the one with velocity close to 0, but
I see.
I think that is up. Yeah, I'm not sure if it is the up right or the.
I think it's the one below, because M87
right?
is the one below. Yeah.
Okay.
Yeah, I'm sharing my image of the Virgo cluster. Oh, I'm not sharing. I'm looking at it. I can share it if you like.
Do you want to share screen, Raya?
I'm wondering if I should for a moment. Just give me a moment and I'll share my screen,
sure.
and I'll take it back.
Okay.
So, okay, I'm going to share my screen, and this is the image that I'm seeing. So this is M87 up here. You can see my cursor, and then this I think is M49, Lisa, and then this I believe is M86 down here. And this is the full cluster. Let me see. I'll zoom out so you can see the whole cluster. Yeah, now you can see the whole cluster. I don't know what happened to my navigational bar, the one that lets me zoom in, zoom out. But I believe this over here is M87. You can see a lot of globular clusters around it. And this is M49 up here. And then if I pan downwards, quite a long way south, is M86, this one here. You see these amazing ghosts around the bright stars, but we're probably looking at a DE that's close to this one. Not probably, we are right now. Oh, there we go. Now I can navigate with the navigational bars. So that's at the center of the screen is M86. And then if I pan upwards, the center of the Virgo cluster is this galaxy here, M87. Right, Elisa, this is M87 here, right?
Yes.
And one can zoom in a long way into this. You can see the jet in M87 going out this way. There's a massive black hole at the center of this thing. Supermassive black hole. This is a very photogenic black hole. This is the one that was imaged right before the pandemic. That black hole was imaged with the Event Horizon telescope, the black hole at the center of this galaxy. This is called Messier 87. And then in the upper right here is M49, this galaxy. And then there's this crazy galaxy here that is being RAM pressure stripped. Very, very beautiful. It's falling into the cluster and it's it's almost like if you stick your hand out of a moving car, the wind tries to blow it back. And this galaxy is, as it's falling in, by virtue of its own motion, just like by analogy, by virtue of the car's motion, the hand experiences sort of this backward force from the wind. Same thing here, the galaxy is falling into the cluster, it experiences this wind because of the speed of its motion. And so part of it is being blown back, almost like a dog having its ears blown back in the breeze. These are the two ears of the dog. Okay, Lisa, I'll stop sharing if you go back to your screen share. And I want to answer one of Tim's question from the chat. Tim, you had asked whether we're using adaptive optics. We're not. And for the work we are doing today, the galaxy is actually quite extended. So we're not trying to get a sharp image of it. It's a very fuzzy galaxy. Getting a sharp image wouldn't help. What we're trying to do is use the Keck telescope to collect as many photons as possible, so we can take a meaningful spectrum. So for today's observations, adaptive optics would not have helped, would have actually hurt, because adaptive optics has lots of reflective elements. So there's a lot of light loss in those. So and what you get as the benefit, the cost is the light loss, but what you get is the benefit is very sharp images. But since these galaxies are quite fuzzy to begin with, intrinsically fuzzy, taking sharper images wouldn't make them wouldn't make them look any different. Yes, the galaxy is falling into the center of the Virgo cluster because of the gravity of Virgo. Yeah, the wind is indeed caused by friction with what is called the intergalactic medium, or in the case of a cluster, it's called the intra-cluster medium, ICM or IGM. Intergalactic medium is the medium that's in the space between galaxies, but since these galaxies are part of a cluster, it's the intra-cluster medium. Jim, does that answer your question? Great.
So we didn't hear the sound then. So we do not have sound. I don't know.
You don't have sound, okay.
I don't know why my sound is not working.
You're not hearing it on your computer, is it?
No.
Okay. I see the sounds app is open.
Yeah, and now I am there because I didn't manually in the terminal, but for some reason the exposure finished and the readout finished, and I didn't hear anything.
One thing I just noticed is the countdown of the seconds. That was frozen for me for a while, and now it's starting again. In your screen share, next in the green box that says object 413414. This is the one that's counting up. For a long time that was frozen, and then now it's dynamic. But that doesn't explain why you're not getting sound, because that's only the Zoom part. That's the
Okay.
So this is now the second exposure, second half-hour exposure, I guess.
Yes.
Yeah, I mean the intergalactic medium is, it's less dense than the best vacuum we've created on Earth, but it still exerts friction. And it's also true that the galaxy is moving at a very high speed, very, very high speed. We're talking about hundreds of kilometers per second, a few hundred kilometers per second. That's a typical speed within a cluster. Hundreds of up to 1,000 kilometers per second. It's almost certain that ram pressure is triggering the formation of stars. It's causing gas clouds to collapse as it gets shocked by the intergalactic medium, and then that's causing these gas clouds to collapse in the galaxy and produce stars. It's almost certain that that's what's going on in that galaxy. Lisa, Joel will be doing the second half of the night, is it? Or will you will you do a handover to him at some point?
I'm not sure if I'm gonna stay. He will join, and I'm not sure if I'm gonna stay or
If
I
you
will.
stay, yeah, that makes sense. Yeah, and Tim has asked, these are very old galaxies, so the star spectra are expected to show low metallicity. Yes, they're significantly lower metallicity than our sun, significantly lower. Right, Elisa, the typical metallicity is what, -1?
Yeah, something like that.
And -1 is in logarithmic units, so that means 1/10 of the metal content of the typical stars in these galaxies have 1/10 the iron to hydrogen ratio as the sun. The sun's ratio already is only 2%. These things are more like 0.2%, so 10 times lower.
So did you answer, Raja, why aren't most galaxies bent like that, referring to the intergalactic medium? Because that's a very good question, actually.
Why aren't most galaxies bent like that? That's a very good question, right? Yeah, I don't think we know. I don't think we completely understand. One thing we can't see in all of this is three-dimensional depth of these galaxies, that is where they are along our line of sight. So it is entirely possible that that galaxy that's so badly bent, it has a particularly high relative velocity relative to the cluster, and it may be in a particularly dense part of the cluster. This plasma, this ionized gas that causes this friction, is hard for us to see in the optical. It shows up in other wavelengths like X-ray, etc. So I suspect it's some combination of how fast it's moving, where it is in the cluster, and how much of this interstellar medium it is encountering. The final factor that I think is making that galaxy look spectacular is this galaxy, the one that we're seeing, the one I was showing earlier with the sort of blowback ears, that still has a lot of the raw material that galaxies need to make new stars. And it's these gas clouds that are affected by ram pressure. Individual stars are not. Individual stars are like bullets moving through air. They don't experience much friction because they're a very high density. They're compact. Individual stars are compared to gas clouds. So I think one special about that galaxy is it still contains a lot of the raw material required to make stars, and that material is what's getting blown back. That's creating new stars. Many of the galaxies in the Virgo cluster have already lost their fuel, have already been ram pressure stripped. So this galaxy could be falling in for the first time. It's not like it's made many passages through the cluster, whereas most galaxies that we see in the cluster have made many journeys through, and they've sort of been stripped of all their material through the process that you're seeing in this one galaxy. This is all speculation on my part. I don't know for certain that that's why we're seeing it in this galaxy and not in others. Elisa, what do you think?
Yeah, no. So yeah, I agree. So to be ram pressure stripped, you need to have gas. So we think that well, we know that most of these galaxies do not have gas left in them. It's mostly only the stars and dark one. So yeah, that galaxy that looks like it's ongoing, this process is most likely because it is infalling for the first time. Yeah, so the thing is that to be restricted, so it depends on, as I was saying, in which direction you are going, through which year you are going, and at which speed. And yeah, so that information we do not have because we see the sky in 2D instead of 3D. So we do not have all that information.
Yeah, we're missing one of the three spatial dimensions.
Yeah.
And we're missing two of the three velocity dimensions. We can only measure one component of velocity. We can't measure the other two easily. In fact, ironically, the velocity component we measure is along the line of sight. And that's exactly the dimension along which we don't have spatial information.
Mm-hmm.
So if you think of the sky as X, Y, Z, where X and Y are in the plane of the sky, and Z is the axis connecting us to the object, we can measure the Z component of the velocity, but not X and Y, because the X and Y components cause proper motion, and that's just too subtle for us to measure. And in terms of position, we can measure the X and Y positions of the galaxies very well, but we don't know the Z position, the depth of the galaxy along our line of sight very well.
Mm-hmm.
So we measure X, Y, not Z, and we don't measure V sub X, V sub Y, we measure V sub Z. So of the 6 components, 3 spatial, 3 velocity, we measure 3, 2 spatial, 1 velocity. So we have incomplete information.
Oh, this green box timer, this one is our countdown to the observation that we are doing. So we put here 3 exposures of 1800 seconds. So now it's doing the second, and it has 854 seconds left, 52, 51. So it's counting down what we are observing. Yeah. So we have more than an hour to go still on this galaxy before changing to the next one.
Less than an hour, right, Elisa?
Less than an hour, yes.
So an hour, about 45 minutes, half of like we have, yeah, but like 900 seconds are finished of this current exposure.
Yeah.
900 seconds is 15 minutes, another 900 seconds remain 15 minutes, and then that will be followed by a half-hour exposure. Now, the stars in these galaxies are indeed old. We don't see any young galaxies, and this whole notion of pop 1, pop 2, pop 3 is something that astronomers would use a lot in the early days. They're not used as much today. I mean, that sort of people nowadays talk in terms of age and metallicity of the stars in population 1, 2, 3. And these galaxies, certainly the stars in these galaxies are both old and they are relatively chemically anemic, but 10 times more anemic than the sun in terms of iron to hydrogen ratio.
But in any case, no pop 3.
Not pop 3. Population
Yeah, so
3 would be very, very low metallicity, right?
Yeah, exactly. So population 3 are like the very first stars, mostly hydrogen only, right? So those, actually, I'm not sure if they have been found.
Yeah.
So I know they are looking for them in the satellites of the Milky Way.
Oh.
It is very for the stars, and the dwarf galaxies around the Milky Way are also these building blocks. So they are going to be the primordial galaxies in that sense. So that's where these population 3 stars are being looked for. But I'm not sure if there are, I'm sure there are candidates. I'm not sure if there has been any confirmation that population 3 stars be found. So we always measure stars that already have been slightly enriched, so they do not like qualify like this pristine first stars.
Yeah.
That's
I
right,
agree
Raja.
with that. I agree with that.
You're more into the Milky Way science. In the Virgo cluster.
These are more like population 2, right, Elisa?
Yeah?
These are more like pop 2, right? Because they're population 1 are young stars and high metallicity. Population 2 are sort of
exactly.
older and lower metallicity. These are more like pop 2.
Yes.
Again, that terminology is not used very much anymore. It sort of harks back to a time when ages, metallicities were much harder to measure for individual stars. And so sort of this notion of these populations was born. I did want to ask a quick question, Elisa, about the sample. Is this particular galaxy nucleated or not?
I don't know. I will have to look it up.
No problem.
I
didn't know if you knew.
I don't
Yeah,
know.
so these galaxies look like elliptical galaxies. They're smooth. Their centers are brighter than the outskirts. So they have sort of brightness falling off with increasing radius. And if you made a plot, let's say we made a plot of the logarithm of the brightness per unit area versus radius, if you march from the outside in, you see that there's a sort of gradual increase, almost like a power law or exponential increase. But some of these galaxies have an upward spike at the center. So there's an upturn, and almost like a giant cluster of stars at the center of the galaxy. Nuclear star clusters, they're called, or nuclei, they're called, almost like the nucleus of a cell. And that's what I was asking about. You know, some fraction of galaxies have nuclei, and you know, of these dwarf ellipticals have nuclei. Not all of them do. So I guess
Yeah, so here,
Yeah, sorry, go ahead. Elisa,
No,
go
I
ahead.
was going to comment on comment that the Wikipedia says that population 3 is related to high redshift and the early universe. So that is because population 3 are thought to be so we define them as the very first stars. They will form at the beginning of the creation of the universe with the first stars, and we are looking for those that have, you know, that have not evolved into, so have not died, basically. So they are still in the main sequence with the same. So those are very hard to find. So
Yeah.
so it's not that Virgo is not in that domain. So Virgo also comes from. So the galaxies in the Virgo cluster are as old as the universe itself, and it has been evolved. The thing is that finding Virgo basically has been enriched, so we do not find these stars in the galaxies in the Virgo cluster, or at least with the techniques that we have, because in Virgo the thing is that we cannot resolve stars individually, do this age and metallicity study very well, because that has to, so we can only resolve the brightest stars with HST and do photometry, which is less precise than for example, what we are doing here today, that is spectroscopy. That is a different technique to be precise. In Virgo, we just cannot, we do not have the technology to look for these population 3 stars. If they exist, still they should be there, but we do not know. So we know that the galaxies are newly formed based on their age. So when we measure their age, if they have, so they should be young, basically. And these galaxies that we are observing, and most of the galaxies in the Virgo cluster are all very old. But even, you know, age is tricky also, because when we say young, we say that that means not that they have recently formed, but that they are active, that they have been recently forming stars in an active manner. That doesn't mean that it doesn't have stars that are as old as the universe itself. So what we call young is that, and these are galaxies that are actively forming stars now, or they have been actively forming stars very recently. Is not, they do not come from the early universe and are here now. They most likely are, but now they are still forming stars actively, while the ones that we are observing are not. So all of these concepts actually are, you know, a bit fuzzy, in the sense that when you think of age, you always think in an absolute term, that when this was this born, and when we is when the last stars were forming, not the first ones. Okay.
Yeah, so in other words, galaxies don't have a single age, right? Individual stars are born at different times. And as you said, Elisa, dwarf ellipticals, most of the stars, if not all of them, formed quite a long time ago. They haven't formed stars in quite a long time. They ran out of fuel. Sort of related to that whole fuel idea and ramp pressure stripping. Now, planetary nebulae are generally seen when they are associated with intermediate age population, things that formed 2 or 3 billion years ago. And we don't see them in these galaxies because they stopped forming stars longer than that ago. Supernova remnants are associated with even more recent star formation. So no, we don't see those two categories of remnants from dead stars in dwarf elliptical galaxies, just because they stopped forming stars quite a long time ago. In this sense, the other confusing thing about age is when you look at a galaxy that's very far away, independent of when its stars formed or not, the light from that object is very old. The light has been traveling for a long time. So those are two important things to distinguish when you think about age. Whether the light from the galaxy has been traveling for a long time, which tells you that our vision, that how we are seeing it, is information that's backdated. So that's one kind of notion of time. But the other notion is, when did the stars form relative to when we are observing the galaxy? So you can imagine, for example, that when a galaxy is very far away, 10 billion light years away, or 12 billion light years away, there's just no way that that galaxy contains old stars. It cannot, right? Because the universe has only been around for 13 billion years. The galaxy formed after that. And if we are seeing the galaxy as it was 12 billion years ago, the stars in them can't be more than 1 billion years old, which is not considered very old. I don't know if all that makes sense. So again, two notions of age. How long a star has been around, that's one notion of age, that's stellar age, but also the age of the light, how long light has been traveling from that galaxy on its way to us, determines how far back in time we are seeing. That's correct. If the light has been traveling for 10 or 12 billion years, it's very highly redshifted. These galaxies are not highly redshifted. The Virgo cluster is close to us. It's only 50 million years of light travel time, 50 million, as opposed to 10 billion. But some of the most distant galaxies seen with James Webb, of which, there was one of my colleagues was on 60 Minutes last weekend on Sunday. Brant Robertson was on 60 Minutes talking about some of the most distant galaxies found by James Webb. There, those galaxies are indeed about 10 billion light years away. 10 billion. I think the most distant galaxies ever seen are about that, like 11, 12, maybe even 13 billion light years away. A good way to think about redshift, when you say something at a redshift of 10, for example, if you add 1 to the redshift, so let's say something is at a redshift of 1, add 1 to that, that number becomes 2. When something is at a redshift of 1, that means the universe has expanded by a factor of 2 since light left that galaxy, between leaving that galaxy and now. Expanded by a factor of 2, meaning the average distance between galaxies has increased by a factor of 2. So when something is at a redshift of 10, the universe has expanded by a factor of 11 since the time light left that galaxy. Or when people talk about the afterglow from the Big Bang, the microwave background radiation, that dates back to a time at a redshift of about 1,000. So the universe has expanded by technically a factor of 1,001. It's not exactly 1,000, but it's expanded by a ratio of about 1,000 between the time that the universe emitted this afterglow and now.
Okay.
It's a good way to think
So
about
this
redshift.
second explorer finished. So if you want, Raja, we can show.
Yeah, that would be great.
The spectrum. Yeah. So I have to move this new screen.
You had to
here.
change screens. Yeah, that'd be great. Thank you.
Okay.
How do we know when the nearest supernova is? Well, we found supernovae in nearby galaxies in the Large Magellanic Cloud. Oh, beautiful. Lisa, this is so
Okay,
beautiful.
well, 1 second. It's starting. Let me see that it starts. And 1 second. Okay, because I don't have sound, it's okay. Yeah.
It hasn't started yet. Let's wait for it to start. That box goes gray when it's
it started
erasing the
already.
detector. Has it started now?
Yeah, it has started.
But for my
Yeah.
screen, it hadn't yet updated. That's why I couldn't see it. Okay.
But can you see it?
And now it's
Oh,
hidden by
because I put Control-1 on top.
Yeah. No, I
Okay.
can't see it
It
now.
started right before she moved the window.
Okay.
Yeah.
My Zoom must be lagging because I couldn't see it. It was still showing up as gray.
So do you want to describe what we are seeing, Raja?
Sure, sure. What we are seeing here, these sort of curved, mostly vertical bands,
Mhm.
it's almost like reading a scroll. You're supposed to read down each band
From
and
up
then
and
go
down.
to the next. So you start on the far left, you read down the band, and as you march down, wavelength is increasing. And then you move over. These are called orders of the spectrum. This is an Echelle spectrum. So you're moving over. So I think the leftmost is order 14 or order 15. I think it goes from order 6 to order 15. So let's see, 6, 7, 8. So order 6 is on the far right. Far right. The band on the very far right is order 6, I believe. That one is order 6. Elisa has a cursor on. Then order 7, 8, 9, 10, 11, 12, 13, 14, and 15 is very faint because,
Yeah.
We're talking about very short wavelength light, ultraviolet light, near ultraviolet light, and these galaxies, because they have they have old stars, they don't put out much UV light. So you can barely see the galaxy in order 15, but you can see it in order 14, and certainly 13, 12, etc. So the vertical streak that you see through the middle of each band, that's the central part of the galaxy. It's brightest there. That's the nucleus of the galaxy, or if it doesn't have a sharp nucleus, it's the central part of the galaxy, the brightest part of the galaxy. That's what you're seeing in the center. Now, because these galaxies are made up of stars, like the sun puts out light at a wide range of wavelengths, not just one wavelength, wide range of wavelengths. So that's why the spectrum extends very long way vertically. The galaxy is putting out light at all wavelengths, essentially. So you're supposed to read down, if you want to increase in wavelength, you read down one order, and then you step an order to the right and read down that, and so on. So the longest wavelengths are to the lower right of this rectangle, and the shortest wavelengths are in the upper left of this rectangle. Again, order 15 is the shortest wavelength light. Order 14 is slightly longer wavelength, and so on. Order 6 is the longest wavelength light, and it sort of goes from about, in nanometers, from about 0.36 nanometers in the upper left to about 1 nanometer in the lower right. So 0.36 to 1 nanometer, 1.0 nanometers. Or in angstroms, we're talking. Do I have that right? No. What am I saying? That's wrong. 360 nanometers, not 0.36. 360 nanometers, which is what we're talking about ultraviolet.
Yeah, you were
light.
talking
360
microns.
nanometers. Yeah, I was talking about microns, sorry. So 0.36 microns to 1 micron is the range, or in nanometers, 360 nanometers to 1000 nanometers is the range of wavelengths covered by these ESI spectrum. Now, the thing that looks like barcodes, horizontal lines, those are produced by the Earth's atmosphere. The Earth's atmosphere glows at very specific wavelengths. And of course, the Earth's air glow fills the slit. We're looking through a rectangular slit that's 0.75 arc seconds wide and 20 arc seconds long. So the Earth's air glow shows up as images of the slit, rectangles that are the exact same aspect ratio as the slit. So actually not exact same aspect ratio because of something called anamorphic magnification, but they look like rectangles anyway, and that's what those bars are. Now, the Earth's atmosphere puts out a lot of these emission lines in the red part of the spectrum at sort of 7,500, sorry, 750 nanometers to 1,000 nanometers in that range, which is the right half of this or right third of this rectangle. You see a lot of these barcode lines. The line, the really bright line right in the middle of this rectangle is 5577, which is produced by city lights. I bet we're seeing the lights of Hilo here. What is 5577? Is that a Mercury light? Would you happen to remember, Arena? What is 5577? Thought it was a Mercury line, but I may be wrong.
Yeah, I don't have that at the top of my head.
Let me see. What is 5577? Ask Professor Google.
Now you're supposed to ask ChatGPT.
It's oxygen. Sorry, you're supposed to ask that ChatGPT. It's oxygen, actually. It's produced by the atomic oxygen. It's very strong in the glow of the night sky. So it's not human made. It's atmospheric atomic oxygen, single atoms of oxygen, 5577. ChatGPT is only correct some fraction of the time. I think Professor Google is still a little better.
I didn't say you'd get a better answer.
There are so many wavelengths here that I don't even know if I can find any absorption line. I don't see any by eye.
We should be able to see the calcium triplet. Elisa, if you zoom in, so you see that thing that looks like the accordion.
This part?
Let me. Yeah, that is 8660 should be in there.
So is
Yeah,
this
that's
one?
the calcium
And
triplet, exactly. Yeah. What is do you know the velocity of this galaxy? Must be a positive velocity.
I don't know. Does it have a velocity? Oof. So many skylines. This is so hard to.
Yeah, it's very hard to see.
To do
Are you doing vertical cuts?
smaller.
No, it's impossible to see there. But
Yeah.
if you zoom in, if you middle click on that and then hit zoom.
Middle click in here and then. Okay, what happened?
Oh.
Okay.
No, it didn't. It zoomed in, but
But
middle
it
click
wasn't.
should center it on that point, or maybe left click. Just click on that. Yeah, now zoom in. Exactly.
Okay.
You
I think
can
there
see
is
the
an
calcium
absorption
triplet. You
line.
can really see the calcium triplet very clearly.
Oh, gee. So this is one, this is two.
Yeah, no, the
Is that
upper one
right?
is 1, the lower one is 2. The third calcium triplet line is hidden in the accordion.
Oh, okay. So is this two?
Once we sky subtract, we'll be able to see it.
Okay.
So the stronger calcium line is where your cursor is. That's 8542, but
Okay.
redshifted. Looking at that, I would say that's a redshift.
Or
redshift of
blue
1,000.
shifted. Or blue shifted. Because
no,
this
this
is
one-
close to M86.
No, but this one is redshifted. I mean, I can see from the calcium triplet line.
Oh, okay.
I know where the calcium triplet falls when something is blue shifted in Andromeda, for example. That calcium triplet line in Andromeda falls between those two night sky lines, not the lower ones, but the upper two. Right above your cursor, you see those two night sky lines
This
above.
one?
Yeah, it falls between those when it's at 0 or negative velocity. Oh, thanks, Jim. Give me a paper on 5577.
From 1925.
55. Yeah.
Wow, 1925. But
That's
it is
impressive.
atomic oxygen, right?
Yeah, it's saying it's this origin of auroral green line, green.
Green line, yeah. 55 is very much in the middle of the green part of the spectrum.
It's saying, you know, auroras are often green. So I guess that's where that comes from.
Yeah, I see. So just, I guess, magnetic activity in the Earth's atmosphere. I guess that dissociates oxygen. Oxygen normally at sea level is in molecular form, but this is atomic oxygen that produces 5577.
Yeah, I saw another thing that talked about this being like 100 kilometers up in the atmosphere.
Up in the atmosphere, yeah. Because closer to sea level, the oxygen is mostly in molecular form.
O2.
Yeah, so this subject of atmospheric physics, I think it's called aeronomy, not astronomy, but aeronomy. And this is one of the cool things about astronomy, cool or problematic things, depending on how your perspective. When you take a spectrum of something from a ground-based telescope like Keck, you have to disentangle at least three things from one another. You have the effect of the silicon detector, that's what's causing the cutoff on the right edge of this rectangle, for example. But you have to worry about the silicon detector that is actually measuring the light, or more generally, the instrument, the lenses and mirrors and silicon detectors, the signature of that is imprinted on the spectrum. And one has to disentangle that before one can study astrophysics. But also the light comes through the Earth's atmosphere, and there's the effect of the Earth's atmosphere. That's what's producing these horizontal barcode lines we were talking about. So you have to disentangle instrument, which includes silicon detector, telescope, lenses, all of that, spectrograph, from the Earth's atmosphere before you have to disentangle the effect of the instrument and telescope and the effect of the atmosphere before you can study astrophysics. But even the astrophysics is sometimes mixed with the galaxy. The Virgo cluster could have things in the foreground of it in our own Milky Way, and it could have galaxies in the background of the Virgo cluster mixed in. So there's some disentangling to be done there as well. In fact, the press release link that I put at the beginning of the Zoom call, that comes from stars in the Milky Way that are in the foreground of the Virgo cluster. So we've used this data set to actually study the Milky Way. That's what led to that press release in January. I'm so happy we can see the calcium triplet, Elisa. This is great.
Good data.
Good data, yeah.
Do we know the CM that we have?
I don't know. Rina, is it possible to say what the seeing is?
It's been around 0.9, 0.8 on the guider.
Okay.
So I'm guessing natural seeing is around 0.6 or so.
The guider generally reports a higher value than the natural seeing.
Yeah, DIM isn't reporting right now, so I can't confirm, but that's what we've been getting from the guider.
Hmm.
So around 0.6 in the image?
Yeah. Hard to tell, because I think the fuzziness that we're seeing of the spectrum is intrinsic to the galaxy itself. If it doesn't have a sharp nucleus, we're not going to see a point source at the center.
Mm-hmm. So this is the last exposure of this object. So I'm gonna start looking at which one is the next.
15 minutes to go, Elisa.
Mm-hmm. Yeah. So I have and then previous one. So can we start moving when the is being read out or not? Do we have to wait?
Sorry, what was the question, Elisa?
Can we start moving to the telescope to the next object while it is being reading
Yeah,
out, or,
that should be
we
fine.
have to wait?
Yeah. No.
Okay.
I think that
So
should be
the
fine,
moment
right,
the
Arena?
exposure is done, we can start moving.
There's some things that they were asking us not to do during the readout. That was filter changes with Demos. But I don't, Chunsu and Arena can answer this, I bet. That I don't think there's any problem slowing the telescope during readout, right?
Yeah, I don't see any problem with that.
Okay, perfect. So there is an interesting question in the chat.
Yeah, I was looking at that also, Elisa.
Yeah. So I don't think that we see. So I think that from our perspective, the composition of the atmosphere is homogeneous. So in the sense that we always see the same patterns. So we have to definitely disentangle. So we have to much mask because the absorption. So what the atmospheric molecules do is absorb the light. They eat the light that is coming from space. So basically that light is lost. So we know features atmosphere because every time that you take a spectrum, it's there, the same feature, same shape at exactly the same location. So we know where are, and basically we just don't use that region because there is no information from space anymore. It has been eaten by by the atmosphere. So that is basically why we curve in the infrared from the ground, and that's the motivation for James Webb, that to observe those wavelengths, we have to be outside from the atmosphere so that we do not have all those molecules eating specifically the light that is coming at those specific wavelengths. So, but that if the composition is not homogeneous, I don't think that
Yeah. So we are integrating also, right? I mean, we are looking at the integrated effect of the atmosphere, not just any patch of the atmosphere, the whole, the entire line from the
yeah, but this is a specific solid angle, right? But it is
right.
a specific solid angle. Any changes when we look at different locations.
That's correct. In fact, I was going to add two things to what you said, Elisa. One is that the amount of absorption by the Earth's atmosphere, for example, the A and B bands, that depends on two things: how much humidity is in the air, depends on that, the moisture content of the air, again, integrated over the whole atmosphere, not just at sea level. And it depends on how much air you're looking through. When you're looking towards the zenith, you're looking through less air than if you're looking towards the horizon, looking through a larger column of air. So it depends on those two things. But in addition to this absorbing, the atmosphere is also glowing. That's what's producing those horizontal lines in the spectrum. And that also depends on the chemical composition. Now, we don't try to correct for the Earth's atmosphere from first principles by knowing the chemical composition, etc. In fact, we do something very straightforward. We take, Lisa, can you bring control 1 to the foreground for just for a moment, just for this? If you bring control 1 to the foreground, you'll see that the Earth's atmosphere, where it glows with uniform intensity. So it glows by the same intensity at the center of the galaxy as it does at the edges of the slit, at the left and right edge of the slit. We actually take advantage of that to subtract off something constant at each wavelength. And the constant amount we subtract at each wavelength, constant meaning along all parts of the galaxy, whether it's the center of the galaxy or the edges of the galaxy, we subtract the same thing. Because the Earth's atmosphere doesn't care. It's got its uniform intensity along the full length of the slit. So we use the edges of the band to determine how bright the air glow from the Earth's atmosphere is at that wavelength, and construct a sky spectra model, subtract that off. So if you were to take effectively, it's like taking these vertical cuts, but along the left and right edges of the slit, where the galaxy's light is hardly there, and we create what's called a sky spectrum. Sky merely means is a short term for the effect of the Earth's atmosphere. So we make a spectrum that corresponds to the glow from the Earth's atmosphere, then we subtract that off throughout this rectangle. We don't have any sky subtracted version of this spectrum to show you. I have that with Demos. I can show you what a sky subtracted spectrum looks like. These bars go away when you do that. But you do it empirically. You don't use chemical composition information to do this. You just do it empirically. You say that it's whatever the composition is at the time of this exposure, determine the strengths of these bars, and we subtract that off. Sorry, my explanation is being I can see that my own explanation is not particularly clear here. But there's this whole technique called sky subtraction. It's easier to imagine this if you have a star, not a galaxy at the center of the slit. Then we look on the star and off the star. Off the star, we're just seeing the Earth's air glow. On the star, we're seeing star plus atmospheric air glow. So we look off the star so we can measure the atmospheric air glow. Then we can subtract that from the part where we're seeing star and air glow. When we subtract that off, we're only left with the star spectrum. So lots of good questions, lots of good comments in the chat. Yeah, that's typically how you determine composition. You measure an emission line or absorption line from something, and you try to reproduce it in the lab. And you see what chemical composition and temperature and pressure is required to produce that kind of emission line. So this exposure's got 5 minutes left, or less than that left.
Mhm.
4 minutes. Is that is that the first of 3 exposures, Lisa? This one?
This one is the last of 3.
Last one, okay. Oh, and you've
Yeah.
decided we'll go to row 5 next?
Yes.
Oh, not row 5. Oh, is that the one that's highlighted?
Yes. Row 5 is the next target.
And row 7 is what we're observing now?
Sorry, what?
Which one are we observing now?
Row 6.
Row 6, okay. Okay.
Mhm. Good data.
Yeah, it is very good, very good. Thanks, Tim. See you later.
Thank you. Thanks for joining.
We have several familiar faces in the Zoom call today. So Jim connects quite frequently, so does Robert. Elisa has connected several times from South Africa. Jim and Robert, one of you is in California, one is not. Are you both in California?
I'm in California.
Oh,
I am in California too, yeah.
oh, okay. Robert, you're in Southern California, as I recall, yeah.
Yes.
And
I am too. I'm just about 5 miles from JPL.
oh, you are, okay. Okay. Robert and I have actually met in person in Southern California, thanks to Shadow the Scientist. So this is Annalise and I have never met in person, but she's in South Africa. Let's see, Darsh, Emilio, maybe I'm meeting you for the first time, I think, on Zoom. And Ted, we've met in person also, right? Ted, I think you're based in Shanghai, if I'm not mistaken. We are going to meet in person next month.
This is my first time here in quite a while. I've missed it. I think it's been almost 6 months.
We've had a bit of a lull. We had very bad weather at Keck in February. We had no observing in, we had very limited observing in December, none in January.
And I think there were some that were like 5 in the morning.
Some bad weather in March. Yeah, there was that too. Very different odd times. But now we have coming up in April. This is the first of 4 nights in April. And then we have 2 nights in May and 2 in July. We don't have anything scheduled in June at this point. But we have asked for a bunch of time in the fall. If we get that, we'll have a bunch more STS sessions.
Yes. So Arina, which is not
Shadow the Science. Yeah, sorry. Go ahead, Elisa.
oh yeah. So we are ready to move.
Okie doke. I'll slow down.
Oh. Yeah, there is a panic button in the screen. I don't want to test it. So
Yeah, no, it stops everything. It just stops the exposure.
Okay.
You know, our social media presence with Shadow the Scientist is increasing. So Jamaica put this on Eventbrite. So Emilio, I'm glad you found out that way. This is good to know.
Okay. That may be the one.
So same thing, just center up the galaxy on the slit.
Okay.
Elisa, you want me to just center up the galaxy?
It's
On the
already
slit?
there?
No, not yet. I just want to make sure you want it centered up on the slit.
Yeah, yes.
Okay.
Okay. So if I don't change the exposure time, I don't have to do update CCD,
That's correct.
even though I other parameters.
The
That's
only
correct.
time you have to update it is if you change the number of exposure or the exposure time or the binning.
Okay. Okay.
Anything in that far right box, if you change the mode of readout, the ops type, any of those things,
Okay.
if you make any other changes, like in the filter or slit width, then instead of update CCD, you hit the move button. That moves things like filters, decors, all those things.
Mhm.
You see where it says the word CCD above the rightmost box?
About which box?
In the GUI, in the
We are
main GUI.
centered up and guiding, so we're ready to
Okay.
go.
So expose. So CCD here?
Yeah. So update CCD updates anything that's in the box below it.
Okay.
Ops type or exposure time.
Okay.
I think it's only when you change those that otherwise it stays grayed out.
Okay. Okay. Ongoing.
Very good.
So you have Tuesday and Wednesday too, Raja?
Yes, first half nights though.
First half. Okay.
First half only. And that's for a UCD project with Kaishang and Eric. But the thing is, I'm in Tucson for these all-day meetings on Tuesday and Wednesday. So I'll be in meetings during the day, sleep after that for a bit, then fortunately it's
Okay.
first half night, so they end by something like 3:30 in the morning, California time. I hope things keep rolling smoothly like this, Elisa, with
Nothing
no need for the
happened.
panic button.
Exactly. Yeah. Smooth, please.
Had a share of difficult observing runs. This has been a good one. Touch wood.
Mhm.
Elisa, SIP is getting ready for its 15th summer. This summer we'll have quite a big program.
Mhm.
Looks like we'll have close to 400 students in the program.
Wow.
It's really first. It'll be hybrid for the first time ever. Before it was in person, then it became online. Now it's going to be hybrid.
And how? What is the plan? Some people in, some people online, or
yeah,
for some people is half or.
Yeah, exactly. I think mostly it's that, the third thing, that is for most people, it'll be partly here, partly online.
What happens is that actually the best part of SIP was the community that students created, right? So all of that with
that's
the
a terrific part
online
of it. Yeah,
is
so
gone.
yeah, so that's why we're encouraging students to come to Santa Cruz, even if it's for a small portion of the time.
Yeah, so we have actually a high school institute now at UOP. This is the second year, and we have to participate the astronomy department, well, the physics department, but with an astronomy program for the first time. She's high school students.
Summer school?
Oh,
summer
it's summer
courses?
school.
Summer courses, okay.
Well,
Wow.
it's like a summer camp, basically.
Yeah.
2 weeks summer camp.
Classes or research or both?
It's hands-on activities on topics.
Gotcha.
Yeah.
Wow, that's very good. It's very good.
Yeah. So let's see.
You should invite those students to shadow the scientists, for example.
Yeah, definitely.
So and if they,
yeah,
and invite them to apply to SIP in the following summer if they want deeper, a longer and deeper.
So the thing is that there is no selection here. So there is no. So everybody that applies, if there is a spot, they get in. And right now, we are getting investments from the city of Stockton. That's where our university is located. And from nearby school districts. They are putting millions, actually, so that students, their high school students can go to UOP for 2 weeks and sleep in the dorms and everything. So it's
they're covering the
full camp.
cost of all
they
that?
Stay there. Everything is covered, yes. So then also it's open to, if you are not part of these school districts and you want to participate, you just pay the fee and you can also participate.
I see.
So it's a good opportunity. They launched this last year, and now it has been multiplied, scaled by, I don't even know. So I'm not sure how many students we will have, but many hundreds, many hundreds. So yeah.
Last year, how many did you have?
100 something like that.
Wow.
It was the school district of Lodi. They put all their COVID funds into this, so that the students could socialize more and get, so the idea was gain a little bit of the missed education that was done online, so that they could socialize a little bit more and have a hands-on experience that they didn't have, but now in a
wonderful
university. Yeah, and now the city of Stockton actually has invested several millions on this, and we have, I don't even know how many students coming. Many. Many. So yeah, we are putting a astronomy program. We are gonna be 4 professors teaching that for 2
Got you.
weeks. Yeah,
Got you. Wow,
that's it.
this is fantastic.
Yeah,
If you ever
exciting.
need a guest lecture, I'm happy to do it.
Okay. Yeah.
Or even better, I'm doing a guest lecture for Cosmos. I'm doing which will be in person. And we often do guest lectures on Zoom for SIP.
Mhm.
We can easily invite students. We can easily share the link with students.
Yeah. Yeah, let's be in touch about that. Also.
Definitely,
Yeah.
definitely.
So the 400 in SIP now is all across the university in
All across
departments.
humanities, arts, social sciences, physical, biological sciences, and engineering, everything.
Wow.
I'm offering a project in art this year from someone who's
In
coming
art?
from UCM, actually. Complutensia, yeah,
Oh,
Complutensia.
nice.
There's a visiting artist named Jose Espinel who's coming from UCM, Madrid. He's coming for a year. So he and I are going to co-teach. He does sort of relief sculpture and 3D printing, and I'll be doing pencil drawing and pen and ink. So I'll be teaching particular technique. So
Nice. Interesting.
I've never taught an art class before, so I've never taken an art class. Well, I've taken, but nothing serious in a long time. So it'll be fun.
Yeah, definitely. So Raja, what have you been doing lately? That I see that you are traveling here and there and the other place and all over the world. Is where is Raja? A different country every week.
So I have been traveling a lot, but so this week in Tucson is the this coming week. I guess it's already Sunday here. It is the Aura meeting. Aura is the Association of Universities for Research in Astronomy. So Santa Cruz, UC Santa Cruz is an Aura member, and every member institution sends one rep to this meeting. It's an annual meeting. It's in Tucson every year in April. And then there's an Aura board as well. I'm not on the Aura board. In the past. There'll be, well, even this year, the Aura member reps meet for 2 days, Tuesday, Wednesday, and then the board meets, I think, on Thursday or maybe Thursday and Friday. So I'm here until Thursday morning for this. But I'm also, trying to get Shadow the Scientist to spread to the NOIRLab telescopes. I'm talking to people about that. I'm visiting Eric. I'm visiting Arjun and Joan because we're doing some collaborative projects together on M31, Desi. That's this trip, right? But before that, I was in Oklahoma for a conference, but also for recruiting. We were on Cherokee Nation, recruiting students from Cherokee Nation to SIP and Shadow the Scientist. That Oklahoma trip was, earlier this month. I'm trying to remember, where was I in March? I don't think I traveled very much in March, but I was in Israel for a conference. Elisa, before that, we were in Hawaii to do outreach. So yeah, bunch of travel.
Yeah.
I have a lot more travel coming up. I'm going to the East Coast at the end of this month. May, I'm going to China, to Shanghai and Beijing. June, July, I'm going to Europe, I think, for part of going to Belgium. But then for much of the summer, I'll be here because, except for that Belgium trip, because of SIP.
Mhm.
If you can imagine it, Mila's traveling more than I am.
No
I'm
way.
telling you. And we are trying to interleave our travel because Mila's 84-year-old mother lives with us. So one of us has to be home to babysit. So Mila literally traveling more than I am. We were remembering a time when Mila and I, many years ago, we met at the airport. I delivered a bundle to her as she was stepping off the plane, and just before I was going on the plane. This is before the days of TSA where you could go to any gate, and that bundle was our daughter Tara. So our trip was such that she was arriving, so it was an airport handoff.
Exactly. Here she is. Oh no, where I go.
Yeah.
My goodness.
No, but today's trip was easy because now there's nonstops from San Francisco to Tucson. There it never used to be. For
Mhm.
many years, I had to connect through Phoenix or connect through LA.
That's convenient.
Yeah, it's very convenient. We're planning a big trip to India in August. We do every year because I go with UCSC admissions and we do outreach there. So that's being planned for August.
Nice. So how is Tara doing? Did she start grad school?
Yeah, she's finishing her first year of a PhD program at MIT. So she got admission in her senior year of college while she was at Brown. She deferred by 1 year. And then because of the pandemic, they allowed her to defer by a second year. So she worked for 2 years in New York while between college and grad school.
Is she liking it?
Yeah, sort of. She's liking the research. She's liking classes she's taken. She's finished taking classes. Now it's all research. So they do these very short-term research project rotations. Then she's going to pick a thesis topic.
Okay.
But what she doesn't like is the loss of the freedom she had before. When she was working, she really had her evening and weekends free, but in grad school, you don't get that. So we'll see whether she decides to go through with it or leave with a master's, or yeah, we don't know. I think a lot will depend on how much she enjoys her thesis research, which hasn't started yet.
Oh my God. Oh. At what time does the twilight start?
Morning?
Yeah.
Let me check.
Is it the 12 degree?
12 degree, 18 degree is at 10 minutes to 11 minutes to 5, 4:49. And 12
This
degrees
is
at 5:15.
Hawaii time.
Hawaii
or-
time, yes. Yes. So 7:49 and 8:15. California time. 7:49 is 18 degree, and then 8:15 is 12 degree. And sunrise is at Hawaii time 5:54, so nearly 9 o'clock here. 6 minutes to 9 is sunrise. 6 minutes to 9 PDT is sunrise in Hawaii. So after the shadow session, I might catch some sleep, Elisa, and then come back while Joel is observing.
Okay. Sounds good.
In fact, I think I'm going to close the shadow session in just a few minutes because we're supposed to go to 1:30 California time. We'll close it in a few minutes. Elisa, you remember Patty Shell?
From Santa Cruz?
Yeah, she was the
Yeah.
department manager.
Yeah.
She now lives in Tucson, so I'm meeting with her on.
Oh,
She's retired
nice.
and lives in Tucson with her family here, so I'm meeting her on Monday.
Oh, nice. Wow. She retired so young, right?
Sorry?
That she retired young.
You know, she left our department and joined the chemistry department for a while. And
Okay.
then she retired from there.
Mm-hmm. Nice. So how's everything in Santa Cruz?
Oh, good, busy. I can't wait to step down from my department chair role. That ends
I will
on
be the
June
chair,
30th.
Raja.
You will be chair next?
Yes, starting in July.
Wow, congratulations, condolences, all of those things.
Well, you know, my department is easier than yours. So yeah.
Ah,
So for me, dealing with the professors is the easy part.
I see.
Yeah. We aren't that many, and you know, everybody gets along and all of that.
How
Well,
many? How many faculty in your department?
We are 6.
Okay, but this is physics and astronomy, right?
Yeah, we are actually in the middle of changing the name to physics and astronomy.
Oh,
Yeah.
really? Wow, wow. Okay.
Yeah.
And you and Guillermo are the only 2 astronomers?
No, we are 4.
Oh, who are the other 2?
Particle physicist, another person that doesn't do any research.
I see. Oh, but you're saying that there's a total of 6 physics and astro faculty combined.
Yes. Yeah.
Okay.
Yeah. 6 combined. So with all the travels, how are you doing? All the meetings and all of that?
You know, it's working out okay. I mean, people are so used to Zoom now or hybrid, so it's working out okay.
Okay.
It's not often that we have completely only in-person meetings now. It's either purely Zoom or hybrid.
Mhm. And when your term finish?
When does our term finish?
Yeah, for chair. How many?
Elisa, you got cut up. Sorry, say that again, please.
Yeah, the how many years is the chair position?
Oh, for me, it will be 4.
It will be 4. So how much longer, Roger?
For me as chair, only until the end of June.
There was your
Until the end of June. I started in 1999. So, sorry, it felt like 1999. 2019, sorry. Feels like 1999, but 29. Good
A
Freudian
century
slip.
ago.
Yeah.
Mhm.
2019, I started on July 1st, so it'll be exactly 4 years. But one of the terms, Connie was chair in the fall of 1999. Sorry, fall of 2019 again. I was chair for the summer. Connie was chair for the fall. And then, oh no, sorry. I was chair for summer and fall. Connie was chair for the winter. And she was supposed to have been chair for the spring, but then the pandemic hit and I ended my sabbatical and came back. We came back in the sense of virtual.
Mhm. So who
But
is
so
next?
much. We don't know yet. I mean, there's that we're going through the process. The dean has asked for names from the faculty, and then the dean always nominates, but he's asked for input from the faculty.
Mhm.
That process just started, actually.
Jim Ray and I are talking in a direct chat and exalting your artwork.
Ah, that makes sense. Okay. Because I've been cloned multiple times in this, it's probably confused matters because I got a direct chat, but then I'm actually carrying my sketchbook here in Tucson.
Well, I sent one message accidentally to Chen Su. Did I go to you instead?
I think it went to me instead.
Oh,
I think it might have gone to all of us because I think we're all,
well,
all
no, it
logged
says
in
it's
under
a
the
direct.
same account.
It says it's a direct message because Robert and I've been having a whole conversation here.
But I
We
think
found
there are
out.
many people logged in with my Zoom link.
Right, I
so,
remember when that happened.
Yeah, so I think
Yeah.
we're all getting it.
Well, no, there was just one that I.
Yeah, there was one. Yeah,
accidentally-
there was one that you sent to Chensu, but that also came to me and probably went to Arena as well, right?
Oh, I see. It went to. Okay.
And Elisa.
Yeah. So I was replying to Robert.
Oh, got you.
But Chen is listed. If you look in the pop-up menu, it's listed right above Robert. So I guess I hit the wrong one. So let's see, which one did I? So Robert said apparently you guys met at the a Starbucks in La Crescenta, which
We did.
must be
Yeah.
right down the road from me.
Oh, really? Okay. Because I was there over Thanksgiving last year. I was visiting family there, and we were staying in La Crescenta. So, yeah, I think that's I think that's when we met, right, Robert? That's just like 6 or 7 minutes oh, really?
away from where I am.
Yeah, we met right off Foothill, I think.
I think I know where that Starbucks is. I've probably been to it.
Yeah, so where I was staying is Pennsylvania Avenue, which is which
right. Okay.
runs north-south, just north of the 210, and
right.
Across Foothill, right in the foothills there.
Yeah.
In the Angeles National Forest.
I live by the 134 and the 2, if you know where that is.
I know where that is exactly.
Yeah, I mean, in fact, so I was telling Robert that we could see Adventist Hospital from our backyard, and he said, "Oh, I was born there."
Small world.
Right in that hospital. Yep.
Small world. Yeah. Really.
So it's a very, very small world. So I noticed that I go to the Target in La Cañada quite a bit. That's where my pharmacy is, and I see more people wearing masks there than most places. I always notice that because I'm wearing a mask, and I think it's because JPL is so close. So I think there's more smarter people. People from JPL are going to that Target.
And Robert, I've made some progress on that sketch of the portrait of the girl. I've made some progress on that during my travels in the last few months.
Oh, that'd be great to see. That was a nice picture, as it was even.
Thank you. Yeah, I was actually in Southern California for just one day at the beginning of actually at the end of last month, at the end of March. Meeting up with some colleagues before we went to Oklahoma. So I was that time I wasn't in La Crescenta, but well, we actually went up to the ashram in La Crescenta, but I was staying near LAX. We went up to Griffith.
That's another planet as far as I'm concerned.
I know. We went up to Griffith though, which is not far from you.
No. Well, you're very busy, but if you're ever in this area and have free time, I'd be very happy to meet you.
Thank you, Jim. I'll take you up on that, I'm sure, and maybe meet up with Robert again. And yeah, I have a work colleague who recently moved to Southern California, so we usually meet up here in NorCal. But if I will be making trips to Southern California to meet. I will stop the recording here, and I will